University of Geneva. And I think he's going to tell us everything about 5 p.m.
Thank you. Thank you to the organizer of the meeting, to the Institute for supporting it. The nature of gravitational waves is such that if you detect the same gravitational wave is the same signal of two detectors which are not further parts of the Earth, which are aligned, which is detrimental for the case of having detectors in the Southern Hemisphere. Apart from the little time lag, yes, there is still the case that if you have that, you could have a larger baseline. That is still interesting, and we know there is work about discussing the situation, but of course, the case is weaker, and this is clearly detrimental of this field in the Southern Hemisphere. And indeed, you can see all the detectors are in the Northern Hemisphere. The planned one, almost founded one, like ET and what's the other one? Cosmic Explorer are in the Northern Hemisphere, and so it is a reality. Why, for example, in the electromagnetic case, we must have detectors in the Southern Hemisphere, and there are a lot of them. So it's really more important to have a program like this. So I'm very happy to be here and to do the contribution. Maybe next time we can do it in December. Just saying. But okay, looking forward for next.
Yes, next 2025, the QR QCP should, I mean, almost certain should be here.
That was a nice system, you got it.
Yes.
It was my idea to you had to intervene. So now, before starting business, let me just comment a bit on what a fantastic system. What is fantastic for me is that what they call in general activity. The system is simple enough that allowed us to do next to really go the activation of PM and PM. Yet it is very rich in structure and new emerging phenomena which we discover at the time we go higher in our perturbation study. So I think really the comparison with the hydrogen atom is not so irreverent, especially if you think of the impact that the study of the phenomenology of this object had on the given physical fields for decades. The fact that the electron does not spiral on the proton led us to immediately realize that was something wrong, and eventually to was a smoking gun calling for quantum mechanics. And for the next 50, 60 years, the development followed the phenomenology of the hydrogen atom up to very advanced fields like the vacuum photonation of QED and ER divergences that are at the basis of the study of the Lensing shift. And so also for the complex binaries, the fact that the complex binaries do spiral has been the smoking gun, the first direct evidence of gravitational wave radiation, and now 50 years after the discovery of a double pulsar, and 30 years after the Nobel Prize awarded to this to the shrinking observation of a period, we are here starting to scratching the surface of new relations between this problem and quantum field theory, amplitudes, or what you want to say. And I'm not just speaking of the technological transfer, but really of new insights that this new approach that bring into the field. I felt compelled to say that because from our point of view of GR side, we always start our research proposal, our papers, our talks with a utilitaristic point of view, that is, we have to compute waveforms. Okay, that's how we started the problem. But also for one time, I had just take satisfaction of just stressing that problem. Having this said, for narrative purposes only, yes, we have to compute waveforms after all. And indeed, Maria, the first day of this conference, of this workshop, just told us that the waveform we have not accurate enough, both in the numeric and in the analytical side. I'm focusing on the analytical here, and especially means, I mean, the analytical also was on the ring down, here I'm focusing on the spiral phase, meaning basically the most important element in the spiral phase is the phase of the waveform, and the usual shortcut to compute the phase without having to resolve space-time in non-integrity is just to impose the balance equation. That is, you compute the conservative dynamics. Here, you compute in the linear zone, you compute the radiation field in the radiation zone, the flat zone, you impose balance equation, and on circular orbits, that you will say it is enough to determine the phase. There are two caveats here. First, circular orbits. That means that, well, you can introduce spin if they're aligned, very hard. If they're not, as Justin, I think, told us, then it's a bit of a mess. So we are not considering that precession is not here at the moment. And it will not be in the stock. The other caveat, which I will discuss later, is that there are short terms in the radiation emission, and those you can put them on both sides of the equation, and you just normally they're harmless, but we may reach the point where we should care about them. And last comment I want to say before going on is that if a purpose is, if the angle is building waveforms, the post-Newtonian is the phenomenological element of the scheme. Because ideally, what we want to give to our friends in LIGO is a complete PN level. Okay, PN not so much. Self-force, yes, because of course MYs are interesting, and there is sense in doing that. But in general, I take the attitude that I want to reason by complete PN post-Newtonian levels. Of course, that doesn't mean that the other approach or the other approximation perturbative schemes are not important, because you can use them to compute whatever you want, but in the end, for the purpose of the waveform, you want to organize them on complete levels. So here, you have already seen this scheme a few times in this workshop. There is the relation between PM, I add the self-force. This is a usual scheme, you know. The vertical lines are the PM levels, for example, in the binding energy, with completion date. In the horizontal lines, there are the positive viscosity calculation as coming from amplitudes, or just from completely summed diagrams, including terms in velocity. I want to stress that this is not often appreciated, but there is another dimension in this table, which is normally mentioned in the scattering angle case, but also in the energy. You can see that if you cross Pn and self-force, there is this polynomiality rule. If you express energy in terms of this state frequency variable, it's basically coming from basic algebraic reasons. And also, there is PM also here, because PM works in this way. 1 PM is enough alone to determine all the highest coefficients in every level. 2 PM is enough to determine this, and then it becomes a little bit of the best. So there is a lot of interplay in these relations. Of course, in the scattering angle, this is even stronger. Scattering angle works in the PM-SF plane, so the plane which I'm not showing here. Of course, you can go on thinking in this way. All of these, I will say that now from now on, I will reason by columns, okay? By complete columns. The next slide will be about 2, 3, and 4 PM, a little bit of recap, and then we will dive into the 5 PM dynamics. Okay. Up to 2 PM, basically, the problem has been solved by perturbative solving Astic equation. Okay. The 2 PM was completed by Damoulin as well in the 80s. There was a little bit of difficulty in inventing some operators, but it was basically patched more or less by hand. And then the procedure was systematized. In the beginning of this century, 3pn has been computed with these three methods: the Hamiltonian one, ADM. Again, a improved version of this iterative solution of Eisenhower equation, and then also my surface integral methods. There is also EFT, but it came much later, so I didn't even. The peculiarity of this, the new thing of this level is the appearance of divergences, which have been recognized first with the Hadamard and then better with dimensional normalization. Eventually, these divergences, once they globalize in a proper way, they vanish on the equation of motion. So they don't appear observable. They are gauged away, you can transform them away, and so they are more or less harmless once they are normalized. Not so much can be said at 4pm. I think Riccardo already discussed a little bit this part in his talk, if I remember correctly. Here, there are the first with divergences which are not harmless, which should appear observable if not cured. They are basically infrared divergence in the near zone, which is basically coming from the post-Newtonian expansion, right? I'm drawing them in the EFT style, but it's the same phenomenon appearing in the three approaches which have successfully computed the 4pm. That is the Hamiltonian with a little bit of self-force, or this Fokker-Lagrangian method, which is the descendant of the plane interaction, just done at the Lagrangian level rather than on the equation of motion, and then of course the EFT, which is my field of activity. So what's happening here? It's happening that in the post-Newtonian approach, whatever version you want to choose about it, at least just study the problem in the near zone and in the fat zone, we call it the region. The near zone at 4pm develops these irreducible infrared divergences. And if I just break the theory into sub-theory, each of them is divergent, but if you combine them properly, it is finite. This is really what happens. The near zone has an infrared divergence, this form in the rank. You add the tail diagram from the fat zone, it has an intervallic divergence, which is exactly cancelled the other one, and you are left with a finite number, which is the prediction of the theory. This tiny number can be computed in the initial calculation from the Fokker-Lagrangian and from the EFT. If the RDM, not so much, that's why I had to add self-force, because it provides an extra input which fixes this stuff. Okay? This is the big thing happening at 4p. And also, there is, to remark, since we are in Amplitude last year workshop, this is the moment where I will not even for loop integrals appears in the computation of these potentials. Now, if you are the mood, you just sit down and you solve it. That's what we did. There are, like I remember in one of these papers at 4pm, 3 pages proof of how to do one given particular integral. Okay. If you are me and Riccardo, you just ask how much this does it. That's what we do it. Okay. So we ask Paolo Mastroia to help us because this is what we know. They work in Amplitude, QFT, they must be able to do that. And that's what how we were introduced to this world of reduction integrals, PSAQ, etc., evaluations, and that was how we computed this computation from the FT point of view. Okay, so yeah, maybe it was the first example for me of how Amplitude technology could be useful for these PM calculations. Okay, now let's start for the verified PM. There are basically two approaches to this 5pm. The one, which is also the first in order of time, is the tutti-frutti approach by Pinidamone and Gioralico. Basically, they take different inputs from different calculations, and they unify them thanks to the effective on-body Hamiltonian, which is very flexible and can incorporate inputs from several parts. So basically what they do is they write the most general Hamiltonian given over 5pn. It's the 5pn is written here. U is basically G Newton, and you can have G to the 6, G to the 5, P squared, etc. Okay, these are the way to organize the coefficients, and of course in the central mass you can also organize them by self-force coefficients. Okay, you have this grid. Every point represents more than one coefficient. It's just a schematic thing. Okay, take it from a paper of one of the papers, guys. And then you start. This is the test particle limit, of course, to the one. Then there is a one self-force, and then you start doing the PM here, and then you combine everything. You include the scattering angle polynomiality, and then you end up with the determination of 34 out of 36 coefficients of the 5pm. It's almost complete. Okay, it's almost complete. But what is left is the other part. You know, it's the paper is from 1909. We are in 23, and we are still there. If we had a two self-force analytical computation, that would be it. Okay, but here and there. And by the way, it's worth mentioning that this approach at 6pm also gives a similar thing, and we are basically 4 coefficients short. They are 4 coefficients short. For determining the complete local Hamiltonian. Okay, local is a different thing, can be computed apart. There is a problem on how to define local, non-local. Be careful. I also see a problem here in when you say Hamiltonian, you must say that you are using the conservative dynamics, and I will add a comment about this later. But this is a very powerful approach. And now the other approach is basically start ab initio. You can be done with the PN, with the PM. The PM has been discussed by Mao, I think last week a bit. I will discuss the PN approach. Basically, as we mentioned, it is based on the method of regions. We now have diagrams, now have integrals. The internal propagator is broken, so it is simplified. You start with a Gaussian and you just expand it. Okay, in expansion of instantaneous, semi-instantaneous propagators. And so you just classify your diagrams and your contribution according to how many propagators are full in Gaussian or how many can be just simplified in this way. So we have the potential modes where all the propagators are near zone, including finite size effect. Okay? Just one diagram all the way to constitution. You have the tails, which have been discussed by Ricardo, I think. You have a memory, we have 3 here, three full propagators, and you have the relation gauge, direction squared. This I will comment on it later. Okay, so these are basically the main contribution to the 5pm, and now we are going one by one. Potentials. The complete series of potential models have been computed by Newman and collaborators. It's a lot of diagrams. We have already discussed that this diagrammatic expansion is not the most efficient, and it's a bit redundant. So it's a lot of diagrams, but it's very easy to classify, and you can write the code, which are good enough. And so they did that. It is worth noticing that there is double checks of basically everything, almost everything in the sector. Of course, the first 4 power type to the 0 of G have been double checked because they correspond perfectly with the PN calculation by Bernet. About this one, there is a nice property of main diagrams, which again is called by for the redundancy of this kind of approach. Many diagrams are factorizable, meaning that they are this shape, right? And when they shape, basically one propagator is just on the side. Okay, you can cut this diagram in 2 and nothing happens. And the other just on the side. And this means that this diagram, which apparently is for loop, simplified loop, it is basically for loops. And you don't have to, you can just put it inside your machine like you maybe do the IDPs, master integrals, and everything, or you can just calculate this diagram as a product of two subdiagrams with that coefficient. And this is the order that me and Ricardo took, and William Obadin as well, and Stefano. And the nice thing is that in the static sector, all the diagrams are autodiagramable, so you don't need to do any new calculation to compute them. And that is a nice property which is related to, well, it's too much to say, but yeah, I mentioned that. In the difficulty of integrals in the PM, at least in this sector, no, that is the most difficult one, about the integrals, goes by every 2 PM, okay? So at 2 PM, you need to loop. At 3 PM, you still need to loop because the new diagrams are not factorizable. At 4 PM, you need 3 and 4 loop. At 5 PM, you're still at 4 loop, nothing new, okay? So again, with this property, we could double check. We actually did it first, and then we double check with us through this particular sector. What is left over is the G to the 5. A lot of them are factorizable, and then we checked, and there are just 322. That is to do it. You're welcome. Otherwise, we wait for the 5 PM, which we verify this. So this sector is, I would say, pretty well covered. And now I'm coming to the tails. Okay. We already discussed what the tails are. It is in the radiation, it's just the radiation which scatters on the static curvature of the system. In the self-energy, which is the Lagrange, which you want to do, you just have to close the diagram and compute it. We have a 4 PM, this is a 4 PM contribution, okay? You have this unipole, which cancels the infinite one, you have this constant. Now at 5 PM, you have first of all to take this one and evaluate it next to the derivative. So you set the 1 PM corrected expression for the quadrupole, you set the 1 PM dynamics, and then it. And then also, of course, the other modular terms. And then at the end, you just have to add new diagrams with new multiples, okay? The octupole and the magnetic quadrupole. And about this, just to mention that the magnetic quadrupole, as we normally is written, for example, Thom's power emission formula, is defined only d equals 3. It is not defined because it has a revisity interface. So when you have a dimensional pole here, you better use the formalization of the magnetic quadrupole, which is new tensor, okay? And okay, there is nothing very difficult about that, just a bit of care, otherwise you just don't get the right values, okay? By the way, we know expressions of these tails for every multiple, with all these diagrams for every multiple, in case you want to go up, I get PM. This class of diagrams, so the tails which are sourced by the energy, by the mass of the system, combined with the potential diagrams, they are enough to completely determine the dynamics at first order reversal constellation. Okay, and indeed, it has been checked that if you have this contribution, you go to the scattering angle, it is perfectly okay with the 4 PM calculation of the scattering. Okay, so also this sector is pretty solid. And now there is another kind of tail, which is not even a tail phenomenologically, because it doesn't have a pole, hence it doesn't have non-local terms because they are linked. So it is not really a tail from a phenomenological point of view, it's an instantaneous tail. But we call it a tail because diagrammatically it is the same. It is this self-energy diagram where there is a backscatter by a static contribution, here for the mass and here for the volume. Okay, this is a diagram which has been discussed by Gabriela Meyer last Monday. Okay, which we thought we had computed, but then we realized that there was an issue involving generalized totality and involving the respect of the world identity of the concerned relative radiation diagram. So the talk was the Gabriel was explaining why we had to correct this, and this is now the number. Okay, and we know the number is correct because now this is a piece of action. You can derive the equation of motion. You can derive the angular momentum loss, and this is an agreement with the general relativity calculation. Okay, so we're pretty convinced that this is it. Okay, this stuff contributes to second orders. Okay, it's different also to with respect to the other 10 contributions.
But also the other have, they started once and all, but they
Of course, we have other, okay, but these are enough to complete the. Yes, of course. These also contribute to the new square. Okay. Now I should move to the memory, but now it's a moment to stop for a second and introduce dissipation. So far, we didn't deal about that. The potential are conservative. This is conservative. This diagram contains a little dissipation in the local term, but for the kind of, to meet an accident, you can deal with them using Feynman description. Okay, in the Feynman description, this dissipative term appears as an imaginary part, as usual, and then you have it. It is not always the case, and so we had to resort to the general formalism, which is used to discuss dissipation, which is in formalism. Okay. That is a short summary. You have to double the degrees of freedom, right, of the fundamental Lagrangian. When this integral symbolic integration basically is our diagrams. Okay, we compute the diagrams. We introduce these variables plus and minus. We have the operators now is the retarded one, not Feynman anymore. And on the result, we don't have any more an action, but a generalized action function, which gives us the equation of motion via in this way, okay? Differentiation with respect to x minus, evaluated at x minus equals 0, that means x plus is the physical variable. Okay? That is what we get. We don't get an energy, we don't get an action, we get a generalized action, and in the end we get the equation of motion. Now, for the other system, like in the previous case, where we have basically conservative terms, the final result has the following form, which is the same form of the departure. Okay. Since the starting point was conservative, this form is the form which have conservative physics. So if your final result has this form, the contribution of computing is conservative. So you can forget about this. This is why you didn't use this formalism before. It was just a useless doubling of the effort. Okay. But if this is not the case, you have to use this variable, okay? Because it cannot be, you cannot just incorporate the dissipative dynamics using the final propagators. Okay, so basically, if you want to do the memory, that is this diagram of this and this, you double the degrees of freedom, you have to plus one to variables, that is plus minus variables, and you do your computation. It's not not so difficult. The Feynman rules are the same, the procedure is the same, just keep track of these candidate variables. They contribute also, they start the contribution to new square. We actually computed also with blue line, but that was before discovering this. These amplitude is a problem, and this amplitude is a problem as well. And so we are recomputing. Okay, and once we will have done, we will have almost the complete 5 p.m. equation of motion, which we can test eventually discovering our models. I say almost because there is the last piece of information to take into account, that is the self-energy diagram. This diagram, face value, leading order is 2.5 p.m. It's the usual radiation reaction to the quadrupole emission. Okay, we compute it with the Cabbage variable, if you want. You derive equational motion, which are at exactly this form. Okay, and then the Barton, they use famous Barton reaction force is that you just take this term, you insert in the either derivatives here the acceleration from the Newtonian part, as usual, and you get the Barton. Okay? That is 2.5 pm. But of course, this thing is iterative. If you insert now this contribution inside here, you get the 5 pm contribution, which is a square of radiation reaction. And this is a 5 pm term, which has this form. Okay, and this is the last piece of information. Of course, the coefficients here are known. It's hard to compute, right? At 5 pm, and so this is the last piece of information which we need to for the 5 pm, except for the memory, which we are still waiting for. I would like now to comment about, since we are speaking about dissipative and conservative, of some tricky point which we should pay attention to, which is normally harmless, but we might have been reaching a point where it is not really important. So, another way to decide whether a term is conservative or not is you compute the acceleration, you'd use the mechanical energy theorem, so you just compute the work done by the force, and that is the derivative of some energy, of the energy of the system, okay? So let's just take this as an example, the simple radiation diagram. We just compute the derivative energy is the work done by the radiation reaction force, and we get this result, okay? Because if you remember, this was, you put a V here, this is Q dot, and this is Q dot Q5, okay? Now, if you just open any GR book, you take the Ton's formula and you find Q dot 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 square, okay? Which is not the same thing as this, okay? But almost, because the two contributions are, the difference is the derivative of what's called short term, which has this form, okay? So anytime this thing is not zero or not total derivative, you have an ambiguity. You have a short term which you can put on either side of this equation, okay? Now, in this case, this is practically harmless. First, because this thing vanishes on circular orbits. So for our purpose of computing the phase, it just drops out. Second, because this term is clearly odd in the velocity. There cannot be energy. There's no reason, there's no possibility of mistaking it for an energy contribution, generally, okay? The E is even in velocities, normally, and this is odd, okay? So that we need to separate this. The same thing can be said about the tail, the little dissipative component of the tail diagram, which is no local. So okay, again, it doesn't mix up because it's not local. Okay, but here the dissipative, you just compute this graph. You compute an acceleration, and you compute you do the mechanical energy theorem, and you find that this thing is not a total derivative. Now the question is, how do we break it? How do we separate the dissipative part from the short term, which I can eventually bring on the other side? And in this case, we really can't, because the form of this thing is the same as the back top, okay? Same thing. And you see, if you compute the energy from that, it doesn't even have the wrong part. This term is even in velocities. You cannot tell it apart simply from whatever potential energy will be computed from the potential diagram, okay? I'm not saying this is a problem, but one must be just careful. When you want to compare partial results from different approaches, and you say, I'm taking the conservative part, what is the conservative part? For us, the conservative part is something in the amplitude, the conservative part is whatever is even in velocity. In PM, the conservative part, or in the Moose approach, the conservative part is using fiber. So one has to be And also, coming back to the Wallace equation, E dot equal P gravitational wave, well, if you have a group of people computing E, a group of people computing the power, and you want to link this together, they must agree on what goes on with side. Okay. Speaking of which, oh no, okay, there is just a little bit summary, then I will go back to radiation. So the summary here, what is missing here in the type PM, in the tutti frutti, the two self-force coefficients, and maybe this sympathetic thing which is not very clear to me. In the PM approach, you need, if we go back to our scheme, remember the lines, the rows, 5 PM and 6 PM, you need to do that, but as I was mentioning, there are no really difficult 5 diagrams in this approach. So maybe the 5 PM, I think Mark was talking about them last week, will be somehow ready soon. And for the 6 PM, maybe we can find a trick like we did, because it just if you just want to start at 5 PM part of the 6 PM, maybe you can do that. And it's not clear to me if the memory is included in the scheme. At 4 PM, we have the targeting that it is vanishing. At 5 PM, I don't know. I'll discover a way to incorporate that. In the FT approach, as I was mentioning, we think we have everything except for the memory. And of course, once we compute the memory, we will have to compute the scattering angle and see that the two SF part of the scattering angle is vanished. Otherwise, we have a job. What are the new features of appearing at 5 PM? I would say the memory and the radiation square, certainly, and also this, this mixing of conservative and dissipative terms. To me, they are basically the new things which appear here. I don't see others. I mean, at least which can bring any more difficulties. What expect at 6 PM? Well, you have already have tutti frutti results modulo for coefficients. Again, the PM has done it the first 4 levels. Actually, also the AFT, Bloomberg et al., they didn't only compute the potential at 5 PM complete, but also the potential at 6 PM G to the 4. Okay, so a lot of work has been done here. So to complete that, either you just do 2 SF, I don't know if it will be enough, 2 or 3, or you just go on here and you need to practice an even PM, and according to that rule that I told you before, we have any integrals. So that will be a difficulty because here you genuinely 5 and 6 with integrals, and I don't even know if they know. Okay, so that is some point to investigate. For the rest, I mean, from the Taylor memory point of view, once we have understood how to meet 5 PM, there's nothing you significantly do. Quantitative integrals are the same, just start on multiple, go up in multiples, but it's not a very big deal. Now, I just spent all the time discussing the right side of the balance equation. And since there is nobody in this workshop discussing the radiation from the PM point of view, I took the liberty of making a summary. The leading person in this field is Blanchet and his several collaborators. He's been doing this for decades. The formalism is basically the multipolar post-Minkowski formalism. Okay, so it's again you break the problem into zones. You have a general solution in the fat zone written in terms of so-called radiative moments. You have a general solution in the near zone written in terms of the small moments, which are basically the real moments expressed in terms of the source variables. In the post-Newtonian regime, these zones overlap, and so then you can do the matching. Of course, once you're done your expression, you have insert the dynamic at the creator for PM order, which in this case is for PM. Okay, so it goes like that. You first have to resolve the needs of dynamics, because otherwise you cannot completely solve this problem with zone relation. There are a lot of difficulties here. It's not, I mean, it's very quickly said, but not done, because at 3 PM, the The state-of-state diagrams introduce new ultraviolet divergences, also infrared, but they can be phased away. And this is basically amount to renormalizing the multiples versus the radiative moments in the QFT sense of the world. So it has been done with care. There are certain gauge issues related to reframing, which is computational time, you have to mention. These kind of issues which normally they are harmless, but when you go out into perturbation theory, you have to start worrying about every little things. And the most difficult thing to be done for them was these those diagrams, that is the tail of tail, and the tail of memory of tail, which involved very difficult interventions, but which we managed to do. We published the result in March, I think. Okay, so it's very recent, and along with that, since we know the conservative dynamics at 4 p.m. and the radiative at 4.5 p.m., that is amount to knowing, and we published the phase at up to 4.5. Okay, we have been using 3.5 p.m. phase for the last 10 years, and now this is the new result, and it's really a big step forward. Okay. Of course, I forgot to mention that I didn't include spin here. Okay, but I will have a slide of that in a minute. This is no spin, okay, of course. In principle, this formalism is, and this calculation can be extended without too much pain to 5 p.m. 5 p.m. In the sense that I asked them, I'm not just telling you because I think I asked them, there is, apart from this technical problem, which has already been faced, there are no new features. Okay, so it can really be done with some work, of course, but you just have to do the same one over again. Apart from this, it has to be said that there is also a demonstrative 2-plane calculation in the field theory done by Rothstein and collaborators. In principle, EFT could be used to do that. It's a pity nobody has done it. So if somebody was interested in just telling. I mean, it's a lot of work, of course, but it's straightforward. At least 3 p.m. should be doable. For it's more complicated, but in principle, this is also a viable way to compute this power emission, which otherwise is only one method, and this is okay. And go IPM, which should do the rest of things in factors. Now, spin. This is not my cup of tea. We have many talks by Justin, Ricardo, and Manuel last week. Just saying that since there was some question raised during the discussion last time, I just started this with some research on the weekend. First of all, in the EFT, how we introduce spin, it's just a new Roth-line coupling, okay, which basically gives you +1 p.m. in the value range. Okay, so you do the same thing with this new Roth-line. There are more integrals. You have to pay attention to the spin condition, etc. It's not, I mean, as easy as it sounds. I am just telling you, but okay, you do it. And of course, you have less Feynman integrals at a given PM level with spin, because this is give you +1. Okay, so the integrals are normally less complicated and less spin is. So the spinless case, that's why I'm just talking about that, because first of all, because this is what I know, but whatever thing new feature you find in the case without spin, this is what I'm going to find in the case with spin 1 or 2 p.m. Okay. So that is the situation as far as I understood. You can correct me, if I am wrong. I checked, okay, this is the phase without spin, 3 p.m., 3.5 p.m. until 6 months ago, and now it is 4 and 4.5 p.m. Okay. One spin, yes.
The reason for the zeros?
Yeah, this imagine here. I just didn't write 0.5 p.m.
No, what's the reason for the zeros in between?
Yes, I'm telling you. Here I write Newtonian, and I just, okay, but there's a 0 here as well. I just didn't write, I should write a 0 here. Okay, so there is no emission at there is no 0.5 correction to emission or variation. Okay, there is a 1.5 correction which is the tail. That's why the half integral correction starts at 1.5. This is the tail diagram, but there is no 0.5. Okay.
But like 2 p.m. single power base, 2.5.
But this is 0.5 with respect to the leading.
So in GR, you never have 0.5 with respect to the leading of that effect, which is what this table is telling you.
With 1.5, the other one is given by the spin, and 0.5 because it couples only to the 0i. Okay, so there is an extra term of this. So this is the leading order in spin orbit, and there is simply no 0.5 correction to anything in GR. Okay, that's a 0, and there is a 0 also here, even front to article. Okay, so this is a structure. Okay, so you see, we've been asked 4 p.m. Where are we? I honestly, these two, I just put them light because there is the energy has been computed at the spin orbit. It's also for spin align, of course, align, and also the radiation has been computed. So I don't understand why nobody's bothered just to put them two together and compute the phase. It should be just easy to do. I mean, maybe since a few months ago, this thing wasn't known, so there was no point. So, but I think this is really very, very doable. Okay, and this is also doable.
This has been done.
This one,
Line spin, circular orbit,
Okay.
gravitational wave phase. Leading order spin to the fourth, this has been done.
thank you very much. I was wondering because it's very easy, right? You have the fourth spin already bring you here, and then it's just a few times. Okay, thank you. So I will correct this. This is okay. So to complete the 4 p.m., we need just these two, and I think that it's just a matter of just doing it. Very easy. If you want to go up, of course, there is things are different. I just put 1 or 2 question marks according to what I think is difficult to do. And the rationale is that jump of 1 p.m. are normally difficult. Jump of half p.m. are normally easier because they come from a few diagrams in the radiative cycle, tail of correction to tails. Okay, so this is easier than this because this is 3.5 correction and this is a TPM correction. And the TPM correction is the more difficult, especially because we have the state of tail, which is normalized in multiple various divergences on it to be worked. Okay, so this is more or less a snapshot of the situation. Okay, that would be the end, but since I was full time, I have 3 slides more, which also on the team what a nice system is to polyphonic GL and what can be done by comparing different expansion scheme, like for instance in this case it will be post-Newtonian and circles. So I take my 10 minutes, but probably it will be less. So let's take a different one. The PM just breaks GR into a infrared theory and an ultraviolet theory. Let's forget the ultraviolet. Let's forget the ultraviolet. We just have the theory of multiples in the far zone. We don't know the ultraviolet details. Okay, this is a typical situation in quantum physics. Okay, you do your stuff. Then at some point you find the ultraviolet divergences. You don't know how to cure them because you don't know what happens in the ultraviolet. And so, I mean, there are many approaches to that, but in textbook, the typical textbook thing is that you are the countertop that cancels the divergences and fixes a value of some observable given by some experiment. Okay? And so you end up with a normalization procedure, and you have locks in the energy which come from the fact that you do your matching of your counterterm at a given energy, and then there is an energy, a beta function, and energy scaling of your observable. Okay, this is more or less. And you have all in mind the picture of the running of the alpha in QED, and this idea of the cloud of electrons, where the deeper you go, and inside you to get the cloud, which masks the air charge of the particle, right? And more or less, the similar picture can be done here. Suppose you want to measure the energy on distance of a binary, and this binary emits radiation, and some of the radiation, it's a tail toss, is better scattered inside. Okay, so if you are at this distance, you just see radiation, and if you measure the bonding mass, you don't include this thing into the mass. But if you are far away here, this is just best scattered before your observation point, and you include it in the mass. That is the running. In principle, should give a idea, which is the answer of the mass. Now, in detail, the idea was to formalize by comparing was time. Again, you just have this. You compute T00 from these general generic diagrams. This is the first correction mass, and then you have some ultraviolet contributions, which are basically coming from the tape, which I discussed before. Okay, and so you do the normalization procedure. You ignore the ultraviolet where this comes from. Okay, you do ultraviolet detail of the source, and you will normalize it in the quantum filtering way. So you have a running your energy with the log of the scale when you do the normalization. Now, it happens that also this quadrupole has a similar running, and in this case, the equation is very simple. It's given by this diagram here, tail of tail, and the solution of the running is basically Fourier transform. Can be seen it? Yes. And it's larger. So if I am at a scale u and I'm in Fourier transform, this is given by something like that. Okay, and this is the object evaluated at the double scale. Okay, so that is the running, and I can write this as e to gm omega squared log. Yes, because this was some power here. Okay, just to say that here I have in time domain that becomes some derivatives with log mu, log of the ratio of the scale appearing. Okay, so it's a power series in news, that is these logs which in the end will appear here. So you have this, you have the similar solution, insert the solution of for the cube, this idea, and now you decide you take a choice for the two scales. You say okay, one mu is far zone, the other mu is the near zone. The ratio is the velocity v, basically is x. So you have powers of log x, and you have a contribution. You can solve it. You have a contribution of the leading logs to the binding energy. And that sounds a bit exotic, but if you take n equal to 1, that is the usual log x, which is appear as a tail contribution for the binding energy for the n. It's very well known. Okay, and here we're just summing all the tower. You have a log square term at 7 p.m., a log 10, the log cube at 10 p.m., log to the 4 at 13 p.m. Okay, nothing technological relevant, just fun. And the last thing which I want to say is that you see this is one self-force beyond the limit, because it has only a power on you. And the binding energy in one self-force will be computed up to 22 PN over. So you can just go of the paper. There is a file attached to the Mathematica. There is a lot of stuff. Okay, they computed a complete one self-force terms, while we are looking only for this specific term. Okay, we go there, you look at the coefficients, and we have this one. Okay, I didn't write the 7 PN, but we check also this one. We have 10, 13, 16, 19, 22. We have this number, and all this number fit with the prediction from the normalization. Okay. And now this is really evident.
We have kind
So on one slide you had, great scattering angle test. And did you mean like compute the scattering angle, see whether or not it obeys the polynomiality?
Yes.
Okay. So do you expect it to, or are we sure that it should obey that?
I also would like to.
Sorry, you.
I don't know.
Or what?
Because
I
with
mean,
this question on all the conservative piece, I'm not sure. The argument that the scattering angle should have this rule is very simple and seems compelling, but then I don't know.
or just what is the latest word from Gino about whether or not? Did he say recently that maybe it doesn't? Okay.
I haven't heard that.
Okay. I mean, in a,
If you yes, written in some work, but
I'm
maybe.
not sure.
Okay.
I don't think recollection of someone saying something.
Okay.
No,
Very interesting.
surely we are not in the position to disprove it. That's good to say. Or at least our computation are not disproven that by any.
Well, I mean, when you finish the membrane.
Once we finish, not now.
Right.
So at some point you put in the slide the word pH subtleties, and then you just keep it well.
That's why it's
Subtle gauge issues. Yes. I don't think you really comment on that while you went to the point.
I comment very rapidly. I mean, the frame in which compute this solution and the frame in which compute this solution, at some point they start to diverge to apart. And they have to correct for that. They introduce a new set of momenta, which are called canonical momenta, and then another new set of momenta which correct on them. It's a bit complicated, but I wanted just to mention that it is there are subtle things.
But these are EMS gauges or just standard?
I wasn't reading them with this in mind, so maybe we can read it.
event step